Welcome to The Explainer. So today we're going to tackle a really common question in data analysis. How do you actually measure change? When you try something new, how do you prove it actually worked?
All right, let's just dive right in. You see these claims everywhere, right? This new workout plan changed my life. Or I lost 10 pounds with intermittent fasting. But how do we know for sure? We want to know if an intervention, a diet, a study method, whatever, has a real, measurable effect. It's about moving from just a gut feeling to actual proof.
And to get that proof, science has this amazing toolkit. But here's the catch. You've got to know which tool to use. I mean, you wouldn't use a hammer to saw a piece of wood, right? Pick the wrong statistical tool and you could get a completely wrong answer. So today, we're going to make sure you know exactly how to pick the right one for any of these before and after situations.
Okay, so first up, let's talk about the standard tool in that kit. This is kind of the go-to, the one most people reach for when they're looking at a before and after scenario. It's called the Paired Samples T-Test.
So what does it do? Well, it's built to answer one very specific question. When you look at all the before and after measurements for everyone, is the average change big enough to be legit? Or could it have just been random luck? It's basically asking, did a real significant change actually happen here?
And if you look at these examples, weight, test scores, blood pressure, they all have something really important in common. In every case, you're measuring the exact same person or thing at two different times. And that's the paired part of the Paired Samples T-Test. Super important.
Now, this test is really built for precise, continuous numbers. Things like weight in kilograms or a score out of 100, where the difference between 80 and 81 is the same as the difference between 90 and 91. But, and this is a big but, it's not enough to just have the right kind of data. You also have to play by the rules.
And these rules are what we call assumptions. Honestly, the best way to think about them is like a pilot's pre-flight checklist. It's this crucial list of things you have to check off before you can take off with the T-test. If you skip this step, you're basically asking for a crash landing with your results.
So here it is. This is the checklist. First, your data has to be a random sample. Second, the two groups have to be paired. We just talked about that. Third, the variable you're measuring has to be continuous. Okay, pretty straightforward. But then you've got to make sure there are no crazy outliers that are going to skew your results. And finally, and this is the one that trips a lot of people up, the differences between the before and after pairs have to be what we call normally distributed. They have to follow that classic bell curve shape.
Okay, so that last one, normally distributed, that's often the trickiest. How in the world do you know if your data fits that bell curve? I mean, you can't just look at it and go, looks normal enough. No, we need a real, objective way to test for this, a formal statistical test.
And for that, there's a fantastic tool called the Shapiro-Wilk test. Its entire job, its whole purpose in life, is to check for normality. It's what gives you a straight, objective yes or no on whether your data has that nice symmetric bell curve shape that the t-test absolutely needs to work correctly.
So how does it work? Well, it all comes down to the p-value. Now, with this test, the starting assumption, the null hypothesis, or H0, is that your data is normal. If the test gives you a really small p-value, usually less than 0.05, it's telling you to reject that assumption. So here's the twist. A small p-value is actually bad news if you want to use a t-test. It's a red flag saying, nope, your data is not normal.
So what do? What happens if your Shapiro-Wilk test comes back with a tiny p-value and your data isn't normal? Or what if you have some outliers you just can't get rid of? Do you just throw in the towel? No way. You just reach for a different tool in the toolkit, a more flexible one.
All right, so for those times when your data just refuses to play by the t-test's very strict rules, it's time to bring in the backup plan. And it's a really powerful and flexible alternative called the Wilcoxon Signed Rank test. If the t-test is like a high-performance race car that needs a perfect, smooth track, then the Wilcoxon test is like a rugged, all-terrain 4x4. It's built for the messy stuff. It's designed specifically for those situations where the data is too bumpy for the t-test to handle.
So, when do you use this off-road beast? Well, it's perfect for what's called ordinal data. Think about things like shirt sizes, small, medium, large. There's a clear order, right? But the distance between small and medium isn't necessarily the same as between medium and large. It's also the go-to choice when your numerical data, like weight, just failed that Shapiro-Wilk test for normality.
And check this out. The pre-flight checklist for the Wilcoxon is way shorter. You still need the data to be paired, of course, but look at what's missing.
There's no strict rule about outliers, and most importantly, it doesn't care if your data is normally distributed or not. And that's exactly what makes this test so incredibly useful and robust.
Okay, let's bring this all home. Let's say you've got your before and after data sitting right in front of you. How do you actually make the final call? Which test do you run?
The single most important thing to remember is this. It's not about which test seems cooler or which one you're more familiar with. It's all about which test is the right one for the data you actually have. Your data dictates the choice. And the good news is, it's a really simple decision path to follow.
So here's the final showdown, the ultimate decision tree. First, just ask yourself, what kind of data am I working with? If it's ranked data, like small, medium, large, you don't even have to think about it. Go straight to the Wilcoxon test. If your data is continuous, like weight in kilograms, you have one more step. Check for normality. If that Shapiro-Wilk test says it's normal, you're clear for the t-test. If it says it's not normal, you pivot to the Wilcoxon. It's really that simple.
And that's it. That's the fundamental difference. The t-test is for your ideal, perfectly behaved numeric data. The Wilcoxon is for ranked data or that messier, real-world numeric data. And knowing when to use each one, well, that empowers you to do an analysis that's not just more accurate, but more honest. It's the difference between just getting an answer and getting the right answer.
That's it for this explainer. You now know the rules. So, what story is your before and after data just waiting to tell?